When addressing the grounding of an 800 amp service, especially when a Ufer ground wasn't initially installed, there are several key considerations. Running a ground wire outside the building and back in to connect to plumbing is generally not recommended due to potential safety hazards and code compliance issues. The preferred method typically involves connecting the ground wire to the rebar within the concrete slab. This establishes a direct and permanent connection to the earth ground. If the existing ground wire isn't long enough to reach the distribution panel, a separate supplemental grounding electrode can be used. This can take the form of a buried ground rod or a Ufer ground, if installed subsequently. Now, let's consider some alternative grounding solutions if accessing the rebar by chopping the concrete proves unfeasible. Firstly, there's the option of installing a ground ring. A ground ring consists of a continuous loop of bare copper wire that's buried around the building's perimeter. The service's ground wire can then be connected to this ground ring. Secondly, a grounding plate can be used. This involves burying a metal plate vertically in the ground and connecting the ground wire to it. Thirdly, a grounding strap may be utilized. A grounding strap is a flexible metal strap that can be wrapped around the main water supply pipe or another suitable underground metal object, providing a connection point for the ground wire. It's important to remember that the selection of the appropriate grounding method should be based on a thorough assessment of the specific site conditions and in accordance with local electrical codes. Furthermore, the size of the grounding conductor is crucial for safety and must comply with the National Electrical Code or NEC. Table 250.66 within the NEC provides guidance on sizing grounding electrode conductors for alternating current systems. For instance, an 800 amp service typically requires a substantial grounding electrode conductor, often a 3/0 copper conductor or larger, depending on the size of the service entrance conductors. Now let's dive further into each possible option, starting with grounding to rebar. Grounding to rebar, also known as concrete encased electrode, is considered one of the most effective grounding methods. The rebar, being encased in concrete, provides a large surface area in contact with the earth, ensuring a low impedance path for fault currents. To properly ground to rebar, firstly, locate an accessible section of the rebar within the concrete slab. Secondly, clean the rebar surface to remove any rust, paint, or coatings that could impede electrical conductivity. Thirdly, attach a grounding clamp specifically designed for rebar connections. Fourthly, connect the grounding electrode conductor to the grounding clamp, ensuring a secure and tight connection. When dealing with supplemental grounding electrodes, ground rods are the most common and cost-effective option. These rods are typically made of copper-clad steel and are driven into the earth to a depth specified by the NEC, typically 8 feet. Firstly, select a location for the ground rod that is free from underground utilities and obstructions. Secondly, drive the ground rod into the earth using a ground rod driver or hammer, ensuring that the top of the rod is below ground level. Thirdly, connect the grounding electrode conductor to the ground rod using a grounding clamp and ensure that the connection is protected from corrosion. Now, let's discuss ground rings, which are particularly effective for large buildings or structures with extensive foundations. The ground ring encircles the building, providing a comprehensive grounding system. Firstly, dig a trench around the perimeter of the building to a depth of at least 30 inches. Secondly, lay the bare copper conductor in the trench, ensuring that it forms a continuous loop. Thirdly, connect the grounding electrode conductor from the service to the ground ring at multiple points. Fourthly, backfill the trench with earth, compacting it to ensure good contact with the conductor. Grounding plates provide a large surface area for contact with the earth. Firstly, dig a pit in the earth, ensuring that it is deep enough to accommodate the grounding plate. Secondly, place the grounding plate vertically in a pit, ensuring that it is in direct contact with the earth. Thirdly, connect the grounding electrode conductor to the grounding plate using a grounding clamp. Fourthly, backfill the pit with earth, compacting it to ensure good contact with the grounding plate. Grounding straps offer a convenient way to ground to metal water pipes or other metallic objects. However, it's crucial to ensure that the metal object is indeed in direct contact with the earth. Firstly, clean the surface of the metal object to remove any rust, paint, or coatings. Secondly, wrap the grounding strap tightly around the metal object, ensuring good contact. Thirdly, connect the grounding electrode conductor to the grounding strap using a suitable connector. Let's delve into the importance of proper sizing of the grounding electrode conductor. The size of the grounding electrode conductor must be sufficient to safely carry fault currents back to the source. If the conductor is too small, it may overheat and potentially cause a fire or other hazards. The NEC provides detailed tables and guidelines for sizing grounding electrode conductors based on the size of the service entrance conductors. For example, for an 800 amp service, the grounding electrode conductor may need to be a 3/0 copper conductor or larger, depending on the specific installation requirements. Maintaining low impedance in the grounding system is crucial for effective protection against electrical faults. Impedance is the opposition to the flow of alternating current and includes both resistance and reactance. High impedance in the grounding system can impede the flow of fault currents, delaying the operation of overcurrent protection devices such as circuit breakers or fuses. This can increase the risk of electrical shock or equipment damage. To minimize impedance, use short, direct grounding electrode conductors and ensure that all connections are clean and tight. Additionally, consider using multiple grounding electrodes to create a parallel path for fault currents. When dealing with multiple buildings or structures served by the same service, it is essential to ensure that each building has its own grounding electrode system. This prevents circulating currents between buildings and reduces the risk of ground loops. Each building should have its own grounding electrode, such as a ground rod, ground ring, or connection to the rebar in the concrete foundation. The grounding electrode conductor from each building should be connected back to the service grounding point. In areas with corrosive soil conditions, special precautions must be taken to protect the grounding electrodes and conductors from corrosion. Corrosive soils can degrade the grounding system over time, reducing its effectiveness and increasing the risk of electrical hazards. To mitigate corrosion, consider using copper-clad steel ground rods or grounding plates, which are more resistant to corrosion than bare steel. Additionally, protect the grounding electrode conductors with corrosion-resistant coatings or sleeves. Regularly inspect the grounding system for signs of corrosion and replace any damaged or corroded components. Periodic testing of the grounding system is essential to ensure that it is functioning correctly. Grounding system testing involves measuring the resistance between the grounding electrode and the earth. A low resistance reading indicates a good connection to the earth, while a high resistance reading indicates a potential problem with the grounding system. Grounding system testing should be performed by a qualified electrician using specialized testing equipment. The testing frequency should be determined based on the environmental conditions and the criticality of the electrical system. During electrical storms, lightning strikes can induce high voltages on electrical systems, potentially causing damage to equipment and posing a risk of electrical shock. Proper grounding can help to mitigate the effects of lightning strikes by providing a lower impedance path for the lightning current to flow to the earth. To enhance lightning protection, consider installing lightning arresters or surge protective devices at the service entrance and at sensitive equipment locations. These devices divert the high voltage surges to ground, protecting the electrical system and equipment from damage. The next, specifically Article 250, provides comprehensive requirements for grounding and bonding of electrical systems. It is essential for electricians and electrical contractors to be familiar with the NEC requirements and to follow them carefully when designing and installing grounding systems. Failure to comply with the NEC requirements can result in electrical hazards and code violations. Local codes and regulations may also impose additional requirements for grounding and bonding. Be sure to consult with local authorities to ensure compliance with all applicable codes and regulations. The design and installation of grounding systems should be performed by qualified electricians who have the knowledge, skills, and experience to ensure that the system meets all applicable requirements. Working with electricity can be dangerous, and it is essential to take all necessary safety precautions to prevent electrical shock or other injuries. Always to energize the electrical system before working on it, and use appropriate personal protective equipment, such as insulated gloves and safety glasses. If you are not qualified to work on electrical systems, hire a qualified electrician to perform the work. Regular inspection and maintenance of the grounding system is essential to ensure that it continues to function correctly over time. Inspect the grounding electrodes, conductors, and connections for signs of corrosion, damage, or loose connections. Tighten any loose connections and replace any damaged or corroded components. Keep the area around the grounding electrodes clear of debris and vegetation. Grounding systems play a vital role in protecting people and equipment from electrical hazards. By understanding the principles of grounding and following the NEC requirements, you can help to ensure that your electrical system is safe and reliable. Consult with a qualified electrician to discuss your specific grounding needs and to ensure that your grounding system is properly designed and installed. Remember, safety should always be the top priority when working with electricity.